Let's solve some examples involving joint normal random variables. Uh, let's take a minute to read the problem. Y1 and Y2 are joint standard normals. They have unit variance, they have zero mean, and rho as their correlation coefficient. If we square them, we get two new random variables, as we have seen earlier in this lecture. And what would be the correlation coefficient because of this nonlinear transformation of y1 and y2? So we will call that rho prime. So to start with, let's define y1 and y2 in terms of two independent standard normals, so that the statistics of y1 and y2 are satisfied. So let x1 and x2 be these two individual independent standard normals, and we define y1 as equal to x1 and y2 in terms of a linear combination of x1 and x2, as you see on the screen. And let's just take a minute to make sure that we get what we wanted. So obviously the statistics of y1 is mean 0, variance 1. That's clear. The statistics of y2 is also mean 0, because the mean of y2 would be rho times 0 plus root 1 minus rho squared times 0. And the variance of y2 would again be the sum of the variances of x1 and x2 multiplied by rho and 1 minus multiplied by rho square and 1 minus rho square respectively, and that also checks out to be equal to 1. And what would be the correlation coefficient between y1 and y2? We need to find the covariance, so that would be E of y1 times y2. That turns out to be just rho. From that we subtract the product of the means, which is 0, and we divide that by the individual standard deviations, each of which is 1. So it does check out. So let's now define rho prime in terms of these new random variables y1 and y2. So rho prime, as you see, requires the mean of y1 squared, the mean of y2 squared, the variance of y1 squared and variance of y2 squared, but it also requires the expectation of y1 squared times y2 squared. So we will need to derive them one by one. Let's first get the expectations of y1 squared and also y1 to the power of 4, and likewise for y2 and y2 squared and y2 to the power of 4. For that we are going to use the moment generating function of the standard normal random variable, which we did a few lectures back, and which is exponential of s squared by 2, and the kth derivative of that evaluated at 0 gives me the kth moment, the kth raw moment of y1 and y2. So if we go through the steps, the expectation of y1 squared is 1, which is also expectation of y2 squared, and expectation of y1 to the power of 4 turns out to be 3, which is also the same for expectation of y2 to the power of 4. This would let us write the variance of y1 and y2 squared, each of them, which turns out to be 2. So we have of all the quantities that we needed in rho prime, we have derived most of them. except the one that remains, which is expectation of y1 squared times y2 squared. And that we will now take up. And to do that, one of the straightforward steps would be to write y1 and y2 in terms of x1 and x2. So let's do that. So we square y1, we square y2, and we multiply them when we express them in terms of x1 and x2, and this is what we get. So the expectation of y1 squared and times y2 squared is given in terms of expectations of x1 to the power of 4 and x1 squared, x2 squared, and so on that you see on the screen. We know most of these. Actually, we know all of these because x1 and x2 are independent. So the expectation of x1 cubed being an odd moment is 0 because x is the standard normal. The others we have already found out through the moment generating function. So we can simplify this expression, and it turns out that expectation of y1 squared times y2 squared is a simple function of rho. So it's twice rho squared plus 1. So now we plug this value back in the top expression for rho prime, and the answer turns out to be rho squared. So the nonlinear transformation of y1 and y2 reduces the correlation coefficient between them because as we know, the correlation coefficient measures the degree of linear dependence. So rho prime becomes rho squared, which in the range of 0 to 1 or -1 to +1 is always less than the absolute value of rho. The next example we take up also involves bivariate normals and correlation coefficient. We actually have seen this in the previous lecture, so we won't spend a lot of time on this, but if you want to rederive these, especially in terms of x and y being standard normal, then that would be a good exercise. And let's go through the steps. What we did was we found the mean of A and B and the variances of A and B in terms of those of x and y, and then we started deriving the row between A and B, and for that we had to define a new log normal random variable C, and we went through the steps and ended up with an expression which was definitely different from rho xy, but it would be interesting to see what the answer would be for the standard normals case when x and y are joint standard normals, and you would get the answer as exponential of rho -1 divided by e -1. So that would be the result of this particular nonlinear transformation.